Okay, third and hopefully final video on trig integrals. Now let's just go ahead and jump right in with an example of a definite integral. Okay, let's go 0 to pi over 3 of tangent to the fifth x secant to the fourth x dx. Well, I see the fact that secant here is even and tangent is odd. That means it's going to be really, really awkward if I pull out a secant and a tangent. I mean, I guess I could, and then I would wind up turning all the tangents into secants. It's just more natural for me, at least, to see whether it is possible and, advantageous to pull out a secant squared. And if I do that, I wind up getting that. And the secant squared dx is my eventual du for, all of the u substitution integration that I'm going to be doing. So that winds up being 0 to pi over 3 of tangent to the seventh x plus tangent to the fifth x times secant squared x dx. That means that it's 1/8 tangent to the 8th x plus 1/6 tangent to the 6th x from 0 to pi over 3. Well, the 0 makes this a little bit easier because I know when I plug in 0 for tangent, you don't have to raise it to the 8th, you don't have to raise it to the 6th, it's just 0, right? So really I'm only worried, or I only need to occupy my mind with what happens with tangent of pi over 3, because that's the number that I'm then going to take and raise to the 6th and to the 8th power. Now, most of you probably remember that that is root 3. If you don't, tangent pi over 3, by the way, is root 3. Root 3 to the 8th is the same as 3 to the 4th. And root 3 to the 6th, the same as 3 to the 3rd. That winds up being 81 over 8. 81 over 8. And that winds up being 9/2. I'll go ahead and just do the arithmetic for you. That winds up being 117 over 8. Okay? And while you looked at that originally and you're like, my gosh, it's going to be some like bizarro number. Not really. You integrate it into tangent. Pi over 3 was easy enough to evaluate, and then you move on from there. Okay. Let's go ahead and how about tangent cubed 2x secant cubed 2x dx. Well, both of them are odd, okay? So I can't really pull out a secant squared because then they're still both odd. And how do I get everything in terms of one or the other? This actually cannot, unlike the previous one, this cannot be done both ways. This has to be done one particular way, and that particular way is by pulling out a secant tangent. Now, once I've pulled out a secant tangent, the tangent squared is going to be secant squared minus 1. And then I have secant squared, and then I'm going to have secant 2x tangent 2x dx. Now I'm going to have to tweak that here in just a little bit, but that basically has the makings of my eventual du when I'm dealing with secant. Okay. Now this becomes secant to the fourth 2x minus secant squared 2x. And this right here becomes secant 2x tangent 2x times 2 dx. Well, that 2 needs to be countered, of course, with a 1/2 here out in front. And so what I'm going to get here is when u to the fourth right here becomes 1/5 u to the fifth, it becomes 1/10. Okay, this becomes 1/6 secant cubed 2x, and that winds up being plus c. Okay? Now, let's go ahead and move on to another one. That one was probably easy enough. Let's look at x secant x tangent x dx. Now, if we weren't schooled in all of this, this might actually look a little bit ugly, but we know that this is going to be parts because it's two different classes of functions. Okay? And that's what we have here. Okay? Now this winds up becoming x secant x minus secant x dx, and that actually, you know, it winds up being relatively straightforward. I've already given you the formula for the integral of secant x, and it winds up being that natural log, and so by parts that winds up being like a two-step problem. Okay, not that big of a deal. Let's move on to another definite integral, pi over 4 to pi over 2, and that's cotangent cubed x dx. And you're saying to yourself, oh, that's probably another one of those ones that's going to look like it's going to be a nasty irrational number, but it's going to work out nice and tidy, just like the last definite integral. And I'm here to tell you, no, this one actually is a nasty irrational number, and we're going to have to deal with it as such. I'm going to go ahead and do it the long way, just for the sake of showing you, and then we'll see with the calculator that it is exactly the same. Okay. Now here's the thing. This obviously needs to be pulled apart into cotangent squared and then cotangent. Let's go ahead and see what happens when we use the Pythagorean in order to substitute. We wind up getting pi over 4 to pi over 2, okay? And this winds up being cosecant squared x, cotangent x, minus cotangent x dx. Okay, well, here's the thing. This first one is, the second one is going to be easy enough. The first one, however, you actually have to see that you're going to have to pull the cosecant apart in order to get it into a form that's actually doable, okay? And that winds up being cotangent x dx, still from pi over 4 to pi over 2. Well, here's the thing. This winds up being negative, that winds up being negative, and so that winds up being u du. So what we have here is we have negative 1/2 u squared minus natural log of sine x from pi over 4 to pi over 2. Okay, and now I think you're seeing why this is going to be a nasty irrational number. Basically, sine of pi over 4 and sine of pi over 2 are not really that big of a deal in terms of their values, but then you take the natural log of those, and that's where it's going to get a little bit sticky. I'll save you the torture of actually doing the next step of that. Let's go ahead and look at the integral pi over 4 pi over 2. Give me 2 seconds, please. Okay, and let's go ahead and do 1 over tangent x cubed dx. Oh, whoops. Dx. Okay, and that is the integral that we're looking at, and it winds up being 0.153. 0.153. And I could have done a little extra steps in there in terms of the intermediate, you know, blah 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 blah. But since it's going to work out to a nasty irrational anyway, I figured we should go ahead and cut that short, because the meat of it is not from here on. The meat of it is, do you understand how to change the form such that it is integrable? That's the meat of this particular section. And so since that's already covered, let's move on to the next one. Okay, we've done one similar to this, but it always looks a little bit different when it's in terms of cotangent and cosecant. Okay, now here's the thing. and when it was tangent cubed and secant cubed, they were both odd. You have to remember that the derivatives for cotangent and cosecant mirror the derivatives for tangent and secant, and so the method for changing the form here is going to mirror it as well. You're just going to have a few negatives thrown in there. Well, let's go ahead and if we pull out one cosecant and one cotangent, which is what we're going to want to do. If we're going to pull out one cosecant and one cotangent, you're going to leave them both even, which means that you're going to have a cotangent squared and a cosecant squared. But cosecant cotangent, or at least it's negative, is the derivative of cosecant. So I want to change everything into cosecant. But let's go ahead and show this step first, again, largely because cosecant and cotangent are just a little bit more uncomfortable for us. It's just a lack of familiarity. Okay, here's what I'm going to do now. I want it in terms of cosecant. So this cotangent squared is going to become cosecant squared minus 1. I need a negative right here in order for this to be a proper du. So what I'm going to do, instead of putting the negative out in front, I'm actually going to flip this difference, okay? And therefore my next step is going to be cosecant squared x minus cosecant to the 4th x, and that's going to be u squared and u to the 4th. And here, of course, is my du. And so I'm going to get 1/3 cosecant cubed minus 1/5 cosecant to the 5th plus c. Okay. Now, for the rest of this video, I'm going to do a couple that are just a little bit out of the norm. And sort of walk through. They still are officially trigonometric integrals, although they don't have that same nice and tidy form of, sine cubed times cosine squared or something like that. But if I were to run into something like this looks nasty. Okay, you're like, oh my gosh, it's got tangent and there's secant and they're both squared and it's an irrational expression and I don't know what's going on. And then you remember, my teacher once told me that when I look at a rational expression, one of the first things I should look for is a monomial denominator. And because it's a monomial denominator, and I can separate the fractions, it winds up simplifying to that, which of course by identity becomes that, which of course needs to be changed into that in order to be cosine u du, and so that's 1/2 sine 2x plus c. Looked daunting, wasn't, okay? So just make sure that you don't miss one on a test, either the one coming up in your class or on the AP exam, for a lack of nerve, okay? What you need to do is you just need to go ahead, roll up your sleeves, and just try something, and especially if it's a rational expression, the very first thing you need to look at is a monomial denominator. Okay, let's say that I have sine of 5x, sine of x dx. Okay, that is unlike any that we've seen. It's not that there's different powers, it's that there's different angle measurement expressions, and because there's different angle measurement expressions, we're going to have to use product to sum, okay? Now, I don't know whether your teacher is actually going to ask you to know these and whether one of these is going to show up on the test, but I wanted to at least put one example on the video so that you knew what was going on. It winds up, if you know the identities, it winds up being very, very straightforward, okay? This right here is the one that we're going to use because it's the one that fits our scenario. So sine of 5x, sine of x is equal to 1/2 cosine 4x minus cosine 6x. Okay, so in terms of my integral right here, the 1/2 is obviously just something that I can pull out in front. and it winds up being cosine 4x minus cosine 6x dx. And if I want to change this into two separate integrals in order to deal with the du separately, which you can do, I wind up with 1/8 cosine 4x 4 dx minus 1/12 integral of cosine 6x 6 dx, and that very straightforwardly becomes that. Okay, one last example, and I think from there we're going to go ahead and move on to partial fractions. Let's say that I am given dx cosine x minus 1. Ruh-roh. Okay, the problem here is that is definitely not a monomial denominator. But gosh, I wish it was. So you want to know what I'm going to do? I'm going to go ahead and I'm going to pop a negative out in here, and I'm going to flip that difference. And then I'm going to multiply by the conjugate. And once I've done that, I recognize the fact that that numerator is going to be 1 plus cosine x. That denominator is going to be 1 minus cosine squared x. Now I have my monomial denominator. Okay, my monomial denominator is going to give me cosecant squared x, and it's going to give me cosecant x cotangent x dx. Now if I go ahead and reintroduce that negative into the integrand, I know that that's going to be negative cosecant squared x minus cosecant x cotangent x dx. And now I have the negatives that are necessary in order to just very straightforwardly integrate that into cotangent x plus cosecant x plus c. In these 3 videos, I've tried to hit all the different varieties of questions that I could possibly think of and I could possibly find, while still trying to sort of reinforce some of the stock questions that you're going to wind up seeing. Okay, I can't, in a couple of short videos hit every single possibility. But this is a representative sampling of some of the questions you can see in terms of trig integrals. If you have any questions, as always, please do email me, and be looking also for the partial fractions videos that should be showing up pretty soon. Bye.